Hello and welcome to NCC Group's Cryptopals Guided Tour. My name is Eli, I'll be your guide. In this video we'll be looking at Challenge 13 from Set 2, which covers the ECB cut and paste attack. This attack relies on a trivial property of ECB. As we've seen in previous challenges, each block in ECB is encrypted independently. One thing that this means is that if you reorder ciphertext blocks, the same reordering will be applied to the plaintext. This is a super simple chosen ciphertext attack. And in fact, there are entire generations of cryptographic techniques motivated by these sorts of attacks, from modes like CBC that introduce dependencies between blocks to prevent reordering, to constructs like HMAC that allow detection of modified ciphertexts, preventing chosen ciphertext attacks, to authenticated encryption, which sort of fuses encryption and macking into a single construct. All of these are meant to make this type of chosen ciphertext attack harder, among other things, because these types of attacks, when they are possible, tend to be very dramatic, as we'll see here. So in this specific challenge, we have a toy example of a function that takes emails and returns encrypted user tokens. You could imagine this being part of a web server, like maybe a forum. Each token stores the user's email, user ID, and their role, which is either user or admin. Of course, the oracle will only give us user tokens. Our goal is to use this oracle to forge ourselves an admin token. To do this, let's first isolate the part of the token that we want to replace. We'll do that by extending our email address until our string lines up with the block boundaries. Note that we can still do this even if we can't see the decrypted token, as long as we know the format that it will have, because that allows us to reconstruct its plain text. Now, let's come up with another block. This one will go in the middle of our email, aligned to the block boundaries, and will consist of the word admin, followed by padding bytes. We are, of course, assuming that our oracle accepts these padding bytes as input, that our token serialization and deserialization functions don't object to or modify them either, and that no one at any point checks whether this is actually a valid email address. Which, to be honest, is not a very realistic set of assumptions, but they keep us focused on the part of the challenge that we care about, which is the crypto. And also, to be fair, the padding bytes are valid printable ASCII characters. They're all a white space character called vertical tab, so maybe there's a chance they could get through, although I wouldn't bet on it. Anyway, here's our token, and here's how it is getting encrypted. Since these cipher calls are all independent of each other, we can reorder them however we want, and we can also remove any unwanted blocks too. So let's transpose these two middle blocks and drop the final block, and there you have it. This gives us a valid admin token for our email address. That's right, this challenge actually is just that simple. Now that we've seen it, let's implement it. All right, and here we go. Now let's take a look at the solution for this one. I've once again gone ahead and written this out in advance because this just saves us some time. So we'll start out with the profile parsing functionality, which is essentially this. And this works quite simply. We split on ampersands, and this gives us a list of key value pairs, each of which is going to be represented as a byte string delimited in the middle by an equals sign. It'll give us foo equals bar, baz equals quicks, and zap equals zazzle as byte strings. And then we take each of those, individually split them, and pack that into a dictionary. And this is a little bit funny how I've written this. This is a list comprehension and then a dictionary comprehension around it, which I personally think is the most readable way of doing this, but, you know, a little bit funky to read perhaps. But it really does show you just how expressive Python can be with this sort of byte string mashing, which is one reason why I really, really like Python for writing attack code and why I've chosen to use it for these challenges. There are a lot of languages where this would not be either as terse or as clear, in my opinion anyway. So that's profile parse, very straightforward. Profile build just goes in the other direction. You get there's one eccentricity here, which is that we're taking a tuple of tuples of pairs of byte strings. And this is the Python syntax for that. And we'll talk about why that is in a moment when we get to the later functions. But for now, all we need to really pay attention to is that we're iterating over the inner tuple and constructing key value pairs. And then we're joining those with ampersands and returning the result. The next of our functions is this one right here that takes an email address and does no validation at all on it. I've noted that here, you know, RFC 5322 is what we would look at if we were going to do that validation, but I'd really just prefer to focus on the crypto here, like I said earlier. There's all kinds of extra hoops that we could add to jump through, but the problem doesn't specify them, so I'm not going to focus on them. And so in this implementation, we're not escaping the meta characters, we're just deleting them, which, again, I'm not sure if that's realistic in practice, but who cares? Because truthfully, we're not going to be passing these in our attack code in the first place, and I think this is a realistic way of handling them. So there's that. So we take the email, we remove the meta characters from it if they're present, and then we build a profile around the result. And let's talk about why we're building the profile like this. All right, and let's pause right there for a moment. This is Eli from the future, cutting in with a brief correction. I was about to say that dictionary iteration order is undefined and in practice depends on the output of ciphash. Now, ciphash is a cryptographically strong function that gets initialized with a random seed whenever a new interpreter starts up. This was a nice little tangent because it gives us a chance to talk about the motivation for this, which is hash DOS attacks, and about Python's defense against them, which generalizes quite well and which you can read about in PEP 456. But during editing for this video, I decided to fact check all this, and I was a little surprised by what I found. What I said was correct, but only up through Python 3.5. Newer versions of Python still do use ciphash, but it doesn't influence their iteration order. Here's the history. In versions up to 3.5, dictionary iteration order was officially undefined, and it was left up to implementers as an implementation detail. Different Python implementations could do different things. CPython implements dictionaries as hash tables, and their iteration order reflected this. But in Python 3.6, the implementation detail changed. CPython still used hash tables under the hood, but their new implementation happened to also iterate over elements in order of insertion. And if you were wondering, this does also extend to dict literals. The order in which keys are specified in a literal is preserved as well. This was not documented or required, it's just something they decided to do, but it turns out that this behavior actually has some big performance benefits. And so in Python 3.7, Guido ruled that this behavior should be codified. So the TLDR for this challenge is we could have used a dictionary here as long as we're in Python 3.7 or above, and as long as we've got the key ordering right. Personally though, I'm still fine with the way this was written, even if it could be made terser using dictionaries, because we're being very explicit here about the fact that this is meant to be a ordered data structure. And with that out of the way, let's get back to the challenge. So that does it for the profile for function, and then enc profile here just encrypts the profile under ECB. That's just trivial with PKCS7 padding. And same for the decryption function here. And then we have do evil, which, does what it says on the tin. And this launches the attack precisely as it was described in the animation. We start out with foo@bar.com, and then we insert a padded admin string in the middle of that at the specified location. Technically, this suffix here isn't really necessary because we're not doing any email validations. We don't really care if this looks like an email. And likewise, these could be null bytes for the same reason. But I just thought that, it might be nice to have a little gesture towards realism, even if this isn't going to be particularly realistic. And so I put this in there just to do something to that effect. And yeah, we're going to print out those values, encrypt them, and mash them together. And, this is all fairly straightforward. At this point, you should recognize what's being done here. And the main block at the bottom just, calls that and prints out the result. So let's run this. And let's see if it works as expected. And there we go. Just like that, foo@bar.admin.com, decryption email at foobar.com, and UID equals 10, and role equals admin. Well, so that does it for challenge 13. I hope you found this helpful, and I'll see you in the next one.